we were initially looking at the two assumptions that rationality satisfy, which are completeness and transitivity. We then said that we want to look at three additional assumptions that will help simplify a model, although you don't need them for rationalities, but they're still important in helping and simplifying the model. We talked about the monotonicity property. Now we want to talk about the convexity property. Now, tastes are said to be convex if they're such that when you have two bundles that you're indifferent. Now, the key over here is that you're indifferent between two bundles, right? So you have bundles A and B, and you're indifferent between them. Then, in that case, you will prefer the averages of such bundles, or at the very least, will like averages just as much as these original two bundles. So, convexity property says that tastes are convex if you have two bundles, you're indifferent between them, and their average will then be at least as good as the original two bundles. Either you will prefer it or like it just as much. So, in other words, we can rephrase it like this: averages are better than indifferent extremes. Again, convexity very much requires that the two bundles that we're talking about were indifferent between them. Only then we can apply the convexity property, right? So, indifferent is a keyword here. So what we're saying is averages are better than indifferent extremes, or at least as good as indifferent extremes, right? So the key over here is convexity property says that take two bundles, you're indifferent between them. Their average will be at least as good as these two bundles. Then in that case, convexity is satisfied. Let's look at how do we mathematically formulate this. How do we mathematically write this? So before we write the convexity property mathematically, it's important to note the convexity property is true for all weighted averages of the two indifferent. Again, the key word here being indifferent. The two bundles to apply convexity have to be indifferent to each other. So it's true for all weighted averages. So the weights don't necessarily have to be 0.5. The averages that we talk about in convexity property, it could be any weighted average. So we first need to see how do we represent the weighted average of two bundles A and B mathematically. So the way we can write the weighted average of two bundles A and B, in this case, which are made up of two n goods, x1, x2, so on till xn, is going to be alpha. Then this is bundle A plus 1 minus alpha bundle B. So alpha is the weight that we've assigned to bundle A. 1 minus alpha is the weight we've assigned to bundle B. Like we said, convexity property is true for all weighted averages. The weights don't necessarily have to be 0.5. Alpha could be any value between 0 and 1. It could be that we've assigned a 20% weight to bundle A and an 80% weight to bundle B, or a 30% weight to bundle A and a 70% weight to bundle B. So now that we know how can we define the weighted averages of two bundles, now we can write the convexity property mathematically. Tastes are said to be convex if and only if. So again, it's very important that you're looking at two indifferent bundles, a very key condition. If and only if we have two, what this says that you have two bundles, A and B, that you're indifferent between them. If you're indifferent between them, that implies that the weighted average, again, this is the weighted average that we just looked at, right? This is the weighted average that we just looked at over here. The weighted average of the two bundles is at least as good as the original two bundles, right? So implies that the weighted average is at least as good as bundle A, and the weighted average is at least as good as bundle B for any alpha between 0 and 1, because it could be any weighted average. So this is what the convexity property says, that averages are at least as good as indifferent extremes. And here when we talk about average, we're talking about any weighted average of the two bundles. A warning here, it's important to keep in mind that we can only apply the convexity assumption if we know some pair of bundles we are indifferent between. As mentioned before, it's important that you have two bundles that you're indifferent between. If that is the case, then the average will be at least as good as the original two bundles that you're indifferent between. So the key thing is that you need to have two bundles that you're indifferent between. Then their weighted average will be, then any of the weighted averages will be at least as good as the two original bundles.